Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to talking about biomolecules. And so this part is going to be called Biomolecules Survey Part 1, and it's on carbohydrates. So I want to start out by talking about why this topic is so important. Well, first of all organisms utilize carbohydrates, so they're very important biomolecules. You know yourself that if you are an athlete, you take in more carbs, right? People carbo load and stuff, because basically it's something that our body uses up in order to convert it to energy. And so in terms of nutrition, carbos are more than just starch and sugar. And then in addition, we want to apply previous concepts that we talked about in stereochemistry as well as intro to organic chemistry, where we talk about functional groups, as well as stereochemistry, as well as other structural features. And we're going to see in greater detail how all of this comes together to control biological properties, which is what we're ultimately interested in, right? So first of all, I wanted to talk about the origin of the term carbohydrate. You think about it in terms of carbon and maybe hydrate like water. Well, that's exactly what it actually is, because the general formula for any sugar is CnH2n and then ON, where N is just a particular integer, so for every one carbon you have two hydrogens and one oxygen. And so this can actually be rewritten as CnH2ON. And so this is where we get carbon and hydrate, and this became carbohydrate. And so another thing I wanted to talk about was the different kinds of carbohydrate families that we'll talk about. And so via hydrolysis, which is water breaking, which is when you react something with water in the presence of an acid or a base, it breaks up that particular molecule into smaller pieces. So the first thing I wanted to talk about was monosaccharides. And monosaccharides cannot be hydrolyzed to form simpler sugars. So basically, it's the simplest sugar that exists. And so examples of this is glucose, which I'm sure you've heard of before, C6H12O6. And when you perform hydrolysis on this, where we have water breaking in the presence of an acid, we end up with no change. Basically because glucose is the simplest possible molecule. And now if I do the same exact thing with fructose, which is another form of sugar, which has the formula C6H12O6. So what does this tell you? These are isomers of one another, right? Because they have the same molecular formula. But again, they both have no change. But now, let me talk about disaccharides. In the case of disaccharides, this is a saccharide, or a sugar, that is composed of two simpler sugars. So just think of it like building blocks. You have the simplest possible building block, and then when you have a slightly more complex structure, you're just combining another building block to make that more complex structure. So in the case of disaccharides, you can tell from this prefix, as well as mono, which represents one, that it's composed of two simple sugars. So an example of this is sucrose, which I have an image for you right up here as well. And sucrose has the formula C12H22O11. And this, when reacted in the presence of water and an acid, makes glucose and fructose. So as you can see from this diagram up here, this whole thing represents sucrose, which you can find in sweets, and it's the combination of a molecule of glucose bound to a fructose via a glycosidic bond, which we'll talk about more in a little bit. Finally, we have polysaccharides, which are basically composed of many monosaccharides. These words are so long, so sorry that's taking a bit. Okay, so examples of polysaccharides that are very important are cellulose, that you can find in plant cell walls, and cellulose has the formula CnH2nON. The reason why it's just in this simpler form is because cellulose has a lot of repeating components of this, and so this N value depends on what kind of cellulose you're looking at. And this is basically broken up to many glucose. Another polysaccharide is starch, which again has the same exact formula. What does that tell us? It's just an isomer that's arranged in a different way. Because when you break up starch, you actually end up getting many glucose as well. So we'll see later on in this chapter how the functional groups as well as the stereochemistry actually give us very different biological properties. And you can already see that by looking at glucose and fructose and cellulose and starch.